All right, 16-3 coming up. 16-3. We're going to talk about the synapses now. It starts getting a little. The first parts, the first two parts are pretty easy. It does start to get a little hairy now. All right, so first of all, the postganglionic neurons of the sympathetic division of the autonomic nervous system. Let me say that again. The postganglionic neurons of the sympathetic division of the autonomic nervous system. They secrete adrenergic neurotransmitters, and those neurotransmitters bind adrenergic receptors. So what the heck does it mean to be adrenergic? Well, adrenergic refers to adrenaline and noradrenaline. Now we have another name for adrenaline and noradrenaline. All right, the other names for adrenaline is epinephrine, and the other name for noradrenaline is norepinephrine. So epinephrine and norepinephrine. Those are the neurotransmitters, norepinephrine being secreted due to the sympathetic division of the autonomic nervous system. Both epinephrine and norepinephrine bind to receptors that are G protein receptors. Let me tell you what that means. Right here is a neurotransmitter binding this receptor. It's either norepinephrine or epinephrine. Now what happens is there's a G protein hooked to that receptor. There's actually three subunits to this G protein. There's alpha, beta, and gamma. Let me erase those and write those again a little smaller. There's alpha, beta, and gamma. And really only the alpha one breaks off and floats next door. And when I say next door, I mean, you'll see what I mean here in a second. So when the neurotransmitter binds its receptors, really this entire G protein doesn't float next door, but this alpha subunit right here does. So this is really just the alpha subunit. It floats to an enzyme in the membrane called adenylate cyclase. Sometimes it's called guanylate cyclase. All right. And if it's adenylate cyclase, it catalyzes the reaction ATP to cyclic AMP. But if it's guanylate cyclase, it catalyzes the reaction GTP to cyclic GMP. So we can make cyclic AMP or cyclic GMP, and these are what we call second messengers. So this is a second messenger of the neurotransmitter mechanism. The neurotransmitter is the first messenger. All right, so here's my second messenger. Now it is my second messenger that does the job. Because, I mean, why do I need a second messenger? Because my first messenger doesn't even enter the cell. How can the first messenger do the job if it doesn't even enter the cell? It's kind of like the first messenger is knocking on the door and yelling in, hey, break down glycogen, or whatever the message is. So the first messenger binds the receptor, which leads to the production of a second messenger. And then the second messenger activates enzymes or opens ion channels or turns on genes. So you can see that the second messenger actually does the job and tells the cell to do what the neurotransmitter wants it to do. The second messenger is key here. These proteins, the receptors of the adrenergic receptors are G protein receptors. They all do this, something like this. So some of them might lead to an ion channel opening. Some of them might lead to a gene being turned on. Some of them might lead to a whole bunch of active enzymes. But they all go through this adenylate or guanylate cyclase and uh, elicit the effect. Elicit the effect of the neurotransmitter. All right. Now with the sympathetic neurons, they aren't as specific as the parasympathetic neurons. There's a couple reasons why. One reason is this: the postganglionic neuron here shoots by the effector gland or organ, and it has these varicosities, these swollen areas. This is a varicosity right here. There's the word varicosity. And these varicosities contain the synaptic vesicles. Here's the synaptic vesicle containing the adrenergic neurotransmitters, norepinephrine or epinephrine. That's what they contain. And then these synaptic vesicles exocytosize and release their epinephrine or norepinephrine onto this effector gland or organ or smooth muscle. Now, it, it's kind of like it's bathing the whole organ in neurotransmitter. So it's not real specific. It's kind of bathing the whole thing, and it's not real specific for just this smooth muscle, but instead the entire sheet of smooth muscles. And uh, this non-specific nature of it, there's another reason it's non-specific as well, but I'm not going to get to it yet. This non-specific nature is the reason why the sympathetic division of the autonomic nervous system has certain effects, and we see certain effects from it, whereas the parasympathetic has slightly different outcomes. And I don't mean fight or flight, arrest or digest. I mean in the mechanisms, the specificity. So these varicosities, these bulges in the postganglionic neuron that secrete neurotransmitter, bathes the effector organ or gland in neurotransmitter, and it's not real specific for a cell. Look at this. I might as well tell you right now because it's here. It's upon us. The epinephrine or norepinephrine actually binds two different classes of receptors. We have alpha receptors. That's one class. All right. We have beta receptors. That's another class. We have subclasses. We have alpha 1. We have alpha 2. We have beta 1. We have beta 2. And beta 3 is unique to lipolysis, lipid breakdown. Lipid hydrolysis, lipolysis, lipid breakdown. All right, so we have alphas and betas. Now, typically speaking, the 1s are excitatory and the 2s are inhibitory. So the alpha 1 is excitatory and the beta 1 is excitatory. The alpha 2 is inhibitory and the beta 2 is inhibitory. Now, what you might be doing is scratching your head right now is saying, hey, I want norepinephrine to be always excitatory. Well, guess what? It's not. Norepinephrine is excitatory if it binds the 1s, the alpha 1 and beta 1. And norepinephrine can be inhibitory if it binds the 2s, the alpha 2 and beta 2. So a neurotransmitter may have excitatory effects or it may have inhibitory effects, and it depends on what receptor it binds. Now, by the way, I'm saying the 1s are excitatory and the 2s are inhibitory. Very important word here. Generally excitatory. Generally inhibitory. Generally. So, yeah, there are exceptions to these rules. But let's learn the rule and then we'll learn the exceptions. The 1s are excitatory. That means alpha 1 and beta 1 are typically excitatory. And the 2s are inhibitory. Alpha 2 and beta 2 are typically inhibitory. They don't all use cyclic AMP. Cyclic AMP, calcium. But they all use a G protein. Now, let me go back. Actually, I don't want to go back. I'll muddy the waters if I do. So these all use G proteins. They quite often use adenylate cyclase and cyclic AMP, but they don't always. They could actually use calcium as a second messenger. Calcium's a pretty decent second messenger as well. Look at one other big difference here. Norepinephrine binds the alpha receptors greater than or better than the beta receptors. This is a greater than sign. So norepinephrine has a higher, the alpha receptors have a high affinity for norepinephrine. Norepinephrine typically binds the alpha receptors, more so than they do the beta receptors. Epinephrine binds both of them equally. It binds both alpha and beta equally. So there's what you got there between norepinephrine and epinephrine. All right, so those are sympathetic synapses. All right, so this is 16.3 and 16.4 because I'm into 16.4 now. The parasympathetic division of the nervous system is the craniosacral division of the nervous system. Craniosacral, all right? The cranial nerves that carry parasympathetic neurons are 3, 7, 9, and 10. 3, oculomotor, 7, facial, 9, glossopharyngeal, 10, vagus. You are to learn these cranial nerves. I hope you have them down really good, really well. Now we're going to talk about 3, 7, 9, and 10 from a different viewpoint as parasympathetic neurons. All right. Well, first of all, look at the ocular motor neuron right here. The ocular motor neuron goes to the ciliary body or ciliary muscle of the eye that changes the shape of the lens, and it also goes to the pupillary muscles of the eyes. Now, if I ask you, what does the parasympathetic nervous system do to the pupil of the eye? Think about the saber-toothed tiger. If you're running from a saber-toothed tiger, you want the pupil of your eye to dilate. All right. So the sympathetic nervous system, which kicks in when the saber-toothed tiger is drooling after you, causes pupillary dilation, whereas the parasympathetic division of the autonomic nervous system causes pupillary constriction. When you're sitting on your couch eating potato chips watching a game, you don't need to have dilated pupils. You don't need to see the saber-toothed tiger from a mile away. So you have pupillary constriction. Look at what facial nerve does. The facial nerve goes to our lacrimal glands for one thing. Our facial nerve goes to our salivary glands for another thing. So they go and say, "Hey, start salivating so I can digest." Look at also the glossopharyngeal nerve goes to my salivary glands. You can see that. The facial and glossopharyngeal nerves go to our salivary glands and they cause us to secrete a watery saliva, which is rich in digestive enzymes, salivary amylase. Because there's another type of saliva. There's a very thick, viscous saliva, which the sympathetic nervous system turns on. And this is why your mouth gets so dry when you're nervous, because the sympathetic kicks in, the thick, viscous saliva is secreted, and it dries your mouth right out. But the parasympathetic division of the autonomic nervous system tells your salivary glands, hey, give me watery, enzyme-rich saliva. And then the vagus nerve it wanders. Vagus means wandering. It goes throughout all parts of the body, hits the heart, hits the lungs, hits different parts of your body, hits your digestive tract. So the vagus nerve goes all over the place. It wanders, in other words. Here's the sacral division. Now, I'll tell you the saying. I'll jump ahead and tell you the saying. Look into genitalia. Jumping ahead and giving you something I'll mention later. Point, shoot, score. Well, penile erection, ejaculation, it has to do with the sympathetic and parasympathetic nervous system. Here's how you can tell. Point. Well, that's an erection. As you can imagine, erection points. P stands for parasympathetic. All right. So I'll just leave it like that. So the parasympathetic nervous system goes to your penis and causes vasodilation, causes your penis to fill with blood, and causes an erection. Point. Shoot is ejaculation. As you can imagine, ejaculation is kind of like shooting. And that's the sympathetic, S. All right. And then score is actually somatic. That's also ejaculation. But part of ejaculation is the somatic motor nervous system, and we'll talk about that later. But this point, shoot, score, S stands for somatic. Point, shoot, score, erection and ejaculation. Now, there's a saying to remember the 3 sacral nerves carrying these parasympathetic fibers. And that saying is S2, S3, and S4 keep the penis off the floor. All right. So you can see that S2, S3, and S4 become the pudendal nerve, which goes down to the genitalia and causes vasodilation. So that's the sacral branch of the craniosacral division of the autonomic nervous system. I want you to notice something else. The synapses of the parasympathetic division occur very close to the effector organ. I'm circling all of these. In fact, quite often they occur right in the capsule of the organ. Quite often they do. That means that the preganglionic neuron is very, very long, and the postganglionic neuron is very, very short. That's opposite of the sympathetic division. In the sympathetic division, the preganglionic neuron was likely the shorter of the two. Sometimes they're about equal lengths, and the adrenal medullary route was the exception to that, of course. But quite often, the preganglionic neurons stopped in the sympathetic chain ganglia, which is right next to the spinal cord, and the postganglionic neuron did rest of the traveling. So the parasympathetic division has very, very long preganglionic neurons and very short postganglionic neurons. All right. By the way, excuse me, I'm sorry. Because the synapse quite often occurs in the capsule of the organ, it's called intramural. So the synapse occurs intramurally within the capsule of the very organ it's going to innervate. So now this is not always true, of course, all right, but it's usually true that these synapses occur very, very close to the effector organ or effector gland. This is the collage of the parasympathetic nervous system, the cranial sacral. That's what that is. All right. Now, I'm glad I came back to the collage. Look at my cranial nerves, especially 3, 7, and 9. There's not intramural synapses. They actually occur in ganglia of the skull. These ganglia. So they're not intramural. But look at the rest of these. The rest of these are intramural. So am I being absolute? No. But is it quite often true? Yeah, it's quite often true. I'm circling all the intramural synapses. So there you go. All right, so now let's look at this table. Is a great table. Our adrenergic neurotransmitters, norepinephrine and epinephrine, bind these receptors. These receptors are located here. Here are the responses when epinephrine or norepinephrine bind those receptors. And here's the mechanism. All right. All of them are G protein. Well, most of them are G protein mediated metabotropic. By the way, I'll give you 2 more words. Metabotropic versus ionotropic. Ionotropic. If something is metabotropic, it goes through a second messenger system. If something is ionotropic, it opens ion channels directly. So let me say it this way. The adrenergic neurotransmitters and the adrenergic receptors are all metabotropic. They don't all use cyclic AMP, and I can think of a case where they don't even use a G protein, but they are all metabotropic and use a second messenger. All right, so that's what we can say. Now, I'm going to come down to some ionotropic neurotransmitters right now. The other neurotransmitters are acetylcholine, and these are called cholinergic neurotransmitters, acetylcholine and its derivatives. They bind receptors that are called nicotinic or muscarinic receptors. And the muscarinic receptors are metabotropic, but the nicotinic receptors are ionotropic. So that's what's going on there. We have ionotropic nicotinic receptors for acetylcholine, and we have metabotropic muscarinic receptors for acetylcholine. So that's a good thing. Now I'm going to come back and hit this again in a few minutes. And plus, there's something very important I want to tell you about this. But these are a functional comparison of the sympathetic and parasympathetic nervous system. And what I really want to do is spend some time on this chart right here. But this is a great chart to start studying after I teach you about the preganglionic synapse and the postganglionic synapse. So I will come back to that.